can't reach one or?
No. The thing is, it looks like, okay, so our problem, our homework problem is called as conjecture, right? It's unsolved, right? Idea is that any number, so the conjecture says any number, no matter what number you start, positive number, eventually you will reach 1, right? And it's been tested for very large numbers, right? So your task is to test on some smaller numbers, write a program, you should do it, right? So the question is there a loop? Basic idea is, it's how would you could be extremely famous if you found a loop, right? You found a loop which does not end as 1, right? Because what's happening is all numbers eventually reach a loop 1, 2, 4, right? 1 is odd, times 3 is 3, plus 1 is 4, that's even, divide by 2, you get 2, 2 is even, you get 1. So all numbers so far found end up looping, right? To 1, 2, 4, 1, 2, 4, 1, 2, 4, right? That's the loop where they end up. So they reach 1, right? In simpler ways of stating, right? So that's a break, right? However, right, we don't know. There might be some other loop, right? But well, it so far looks like very unlikely. If you found one, right? I mean, you probably you get you'll be world famous, actually, right? Seriously. But unfortunately, the bad news for you, it's been tested for very truly large integers. So if you go with integers, just regular 32-bit integers, you won't find anything, right? So, but your task is to write simple recursive checker, basically, right? So, only thing what I'll do is I'll make it due in a week. So it's not because it's a simple task. So I think not November. That's be too. All right. Okay. Now, so where's our recursion? Yeah. So again, until now in C++, you've been using just regular iteration, looping, but again, as you know from our algorithms class, right, sometimes the recursive solution will be simpler to write. And again, some of you even wrote some recursive solutions, right?
But just a quick question.
Yes.
The homework you just said, this is the next homework we have to finish. We don't have to.
Okay, I switch. Okay, so let me show you again. Hopefully.
So for the next week we have this one, right?
You have this one. There will be also exceptions homework on Thursday. There will be another homework.
Okay.
Yeah, there will be another homework, right? Because you didn't have any homework last week, right? Yeah, no homework last week, right? So yeah, so there's going to be this simple one today, right? And slightly, I would say, hairier one will be on Thursday, and maybe I'll give you more time on that one. Probably I can even add it right now if you want to get started. But we haven't talked about this, right? It's a little bit messier. I'll do it on. So we'll add Thursday, so 7th of November. 7th of November. If you want to get started on that one. Yeah. Well, not 15th, 7th. No. I don't know why I'm so generous today. All right. So, okay, yeah. Also not too hard, but again, I still want to see comments and so on, right? Now, so iteration today again, like it's just a refresher, right? So, again, the main thing is to remember to define the base case, right? And then some sort of recursive definition, right? What's crucial, it has to be this recursive definition.
Well, it has to change something.
Yeah, well, it has to go to smaller, right? If you keep, at least, right? Because if you check same size problem or bigger problem, you're gonna go up, right?
Yeah.
Yeah. So you're gonna be looping, right? So, right. So, but there's also thing is, of course, we'll talk today about the direct recursion, indirect recursion, right? So, what could those things be? What would be indirect recursion? What do you think? Well, we'll see. Okay. No, don't worry about it. Right. So,
not sure.
Okay, that's fine. Right. So, recursion is solving smaller problem by reducing itself, right? So, base case must be 1, right? At least 1, right? It could be more, right? And general case must eventually reduce to base case, right? Base case stops the recursion, right? So, otherwise we'll never stop, right? So, again, we'll start with our old friend factorial, right? I'll do this first, right? So let me see if I have a notebook ready for this. I think I should. I think I do. No, not here. I have it here. All right, there we go. The structures. So open up a code space. Yeah. So factorial, right? Again, of course, we know how to make it with a loop, right? So again, it's a kind of like a really stupid example, I would say, right? But okay, we'll go with it, right? We'll roll with it, right? So recursion. What do we have? Factory enums, loops. Let's do recursion. Recursion C. Let's explore. Let's explore some recursive solutions to problems. Include IOStream using namespace, right? Let's start with recursive factorial. Okay, thank you, AI. All right, yeah, and it's as simple as that, right? But again, so what's actually happening here, right? So the function, right? When you do this, you are building up the stack, right? There's a stack structure which keeps one stack, particular track, which keeps, well, it has to keep track of all the calls, right? So the big problem, of course, will be if you run out of the space, right? It's limited, right? So what's my plan is, I want to break these things. Let's see if we can break it, right? Let's see if we can break our stack and find the limit, whichever it is, right? So let's recursive, yeah. So this is recursive, right? Fibonacci we'll do afterwards. So let's test int main, right? Right. So this will work, of course. Let's do a hello world, right? G++, val, recursion, and output, I don't know, fact. It works, and we do. Okay, but I am going to add arguments. Since I don't want to do this by hand, we'll do it here. We'll time it. So r count, right? R count, come on, r count, int. Yep, that's exactly what I want to do, right? And we will do our argument. We need two arguments, f and number. Yeah. So, yeah, right. So, if there's no argument 3, right, we return 1 or exit system, how you call it, return errors. We need, let's see, we need something for error messages return or return error code. Well, code, right. Well, I guess 1 for now, but I don't like this particular. I would like to return success, right? Return success, which is 0, right? And again, let's go this C++ reference. Return success, right? Return exit success, exit failure, right? That's the one do, right? Again, of course, they usually are defined as 0 or 1, right? But the whole point is it's CSDD library, right? Here, we'll do that. CSDD. Header for exit. Yeah, we want that. So now we have exit success, exit fail, right? Exit failure, right? Which I think is 1, right? Is it? Yeah, it is 1. It expands to 1. Again, of course, we could have just done 1. Of course, it seems silly, but again, the whole idea is that sometimes it might be a different number somewhere, right? Exit success, right? So this, of course, is more readable, even though we know it's just a 0, right? It's almost always 0, right? But still, okay. But now we want to actually produce. So let's check, right? If f flag, right? So switch we'll do this, switch on flags, we'll do switch. Well, we would like to switch, but we don't really have switch, right? Check, yeah. If, right. So, of course, and this is kind of dangerous, right? So, well, is it safe, right? Right, again. So this means if you didn't do a flag, right? And now finally, we get another fail, right? Now finally convert a second to our integer, a toy, right? Again, we could potentially fail, but still, okay, let's go roll with it on factorial. Now we are cooking. Okay. So this all, of course, has nothing to do with the recursion directly. This is just some extra. We have time to explore some things like the argument count, argument vector. Usually, you want to add these, right? So why do I want to do this? Because I want to don't want to keep adjusting hard-coded code stubs. I want to add user-defined flags, right? So let's compile it, and now I should be able to do this. Factorial usage, very nice. Let's do this flag, do something, right? There's no such thing, right? Very good. So, very nice. So, let's do factorial of 100. What will happen? What do you think will happen? 0. Okay, so why is 0? Let's do this one more time. 5. It's 120. So, how about 20?
Big.
Too big, exactly. Too big. Okay. So what's interesting, at some point it gets 0. I wonder when that happens. So 30, it keeps going. 40, 40 is there. So 35, you're doing binary search, right? You're doing binary search to check, find the error. Okay, 32, 33, okay, 34, and it's 0. It's interesting actually, right? At some moment it keeps multiplying, right? And it gets 0, right? So, again, to get truly large numbers, we will have to add a large number support. So, one thing we can, of course, do, change this to refactor, this to refactor. Yeah, I don't want to do copy, but basically just replace to with double, right? Not double, long, right? Long. And of course, I want to also return long, right? Okay. Long, that looks okay. Let's see, a toy integer. Well, we want to cast to long, right? We can do long, right? So long, let's do that. That should be okay. Let's see if this works. It doesn't, it should. Recursion. All right, that's a pretty big number. 34, so 3, that's millions, billions, trillions, quadrillions. Oh, we still have some space to go. Okay, let's go 40. More negative already. So 38. 38 is still okay. 39 is only, oh no, 39 is still okay. Alright, so 1, 2, 3, 4, 5, 6, yeah. So the limit was 19. So yeah, we're going to multiply by 40 and we end up space. So we don't have direct problem with this, right? But the only problem is we don't have enough time to calculate this, right? So 50, right? So at some point also this will also be 0, right? That's my hypothesis, right? We are just going around. 70, 0. Yeah, so it's interesting. So what was it, 34? So 66. Yeah, 66, 65 will be probably okay still, right? No, 65 is still okay. That's very interesting. That will be something to do, explore why it goes down to 0, right? It's probably because, of course, once you get to 0, that's it, right? You keep multiplying by numbers, you get nothing, right? Okay, well, again, so what I would like, of course, here I would like to do is convert this to something truly large, right? Support truly large numbers. How could we do this? Well, we have to probably download a big num library, right? Use that one, right, to explore it. But because I want to run out of stack space, right? And here looks like we're not going to run out of stack space here because the numbers get too big, basically, right? Okay, so I couldn't really break it. Well, the only way, I mean, I broke it, but not the way I wanted to break it, right? I broke it, so we broke it. So I like to do explore why it goes to 0 around the 65th factorial. Yeah, it overflows around 39th. Yeah, for long. Okay. All right. So we now let's do Fibonacci. And we know Fibonacci is horrible, right? So Fibonacci, we have two base cases. So two base cases. First, we have two base cases. First, we have two base cases, right? And of course, the recursive definition. So what's the problem with this? Who remembers? Why was this bad? Well, we'll see, right?
Well, it creates.
Yeah, it gets 3. It gets a 3, right? We talked about this in our algorithms class, right? So it's kind of bad. Yeah. So let's see both. So this let's do arguments, or we'll do Fibonacci factorial, fib, right? I guess I need sorry about the language, fib, right? I don't know what to say. Factorial, FC, fact, yeah, fib, right? So let's do that, right? So this, of course, this means is this string check is going to be a pain. You see, that's the problem is these low-level C string. That's why it's kind of pain to write. I would like to use this convert this argument to C string. Let's do strings. Import strings. Yeah. Include regular strings from C++. Yeah. Right. So what my plan is, I don't want to do this by hand. This is like I have to do character by character. Amazing pain, right? Of course, there's comparison functions. You could do that. That's also pain, right? That's old school style. So what I'll do is, right? Let's convert second argument to the regular string, to normal string. So string arg, right? Now we can check. Don't have to do this lazy, right? So again, I'm lazy, right? I hope. So now we can check. Now it is easier to check, right? Yeah. So if, all right, welcome back. Or
I'm done.
You're done. Super. You did actually pretty good for data structures. That was fast.
I mean, for this one?
Yeah, I mean, I have not looked at it yet, but I'm saying you did do this fast. Was it good? I don't know.
Hopefully correct.
Yeah. Was it a little bit harder than the?
I think, like, conceptually
Yeah.
it was easier
Yes.
but longer.
Yes, exactly. It is more conceptually. It's really easy. That's why it is not. You don't have to invent a new algorithm, right?
Yeah.
But okay. So we are doing recursion. So very easy stuff, right? So if, right, now we can do this, right? Fibonacci or yeah, we decided fact and fib, right? Sorry, fact factorial, right? Now, of course, YouTube will probably censor me, right? So fib, right? Now we have usage. Again, another trick for programming, of course, in most language, it's a good idea to exit early, right? We exit early. Why? Because then we keep our code flat, right? What we don't want to do is nested if hell, right? Like, right? Don't do this, right? Right? Don't do this. Right? Kalba. This is JavaScript, but it could be applied to many other languages. Yeah. I'm not going to, sometimes you can't escape it. Okay, so now we have our, right. Now we do check, right? And now we need, of course, now. So if argument is factorial, right? And now we have, well, right, so we could we don't even need, we don't need even this actually, right? We could even, right? We could do this actually, right? So we don't need this because we already know, right? So I guess I'll comment this out, right? Because it's here, right? and we don't need this one, right? I would like to, of course, do, this is not, I would like to do some matching switch case. This is like would be a good argument for switch case, but for now this is easy, right? Factorial, Fibonacci, right? We get one or the other. Okay. Now let's do Fibonacci. How much of Fibonacci we can get? How far? Is it long? Did we do a long one? Yeah, we did a long. Okay, long, long. All right. And we now, it should stop by around 32, right? We'll run out of space. Let me. On factorial, I'll do something. Doesn't work, right? So let's do factorial, fib, and I'll do 10. And it works. Super. 20. It works. 30. Still works. 40. Do you think it'll work? Nope. Well, works, but getting slower. Right, let's time it. Right. Let's time it. I think let's time. Right, yeah. Let's time it. Okay, 0.7 seconds again. So we now remember with Python it starts getting slow around 32 or 33. So with C++, well, we get 7 more numbers before it starts getting bad. But it's still tying down to back to algorithms. The problem, I mean, if you have a horrible solution, C++ is not going to save you, right? Because in this case it's a bad solution, right? So let's do 50. I can't do 50, but let's do 42, right? 42 is probably going to get really slow. Yeah, 1.9 seconds. All right, so 43 will be what? 3 seconds. Oh, let's see, 44. 4.5 seconds. 5 seconds. Already getting bad. 45. Bless you. All right, 8 seconds, and it's going to get worse. Okay, one more, 46. You can still do 46, right? On that is okay. That's enough. I think enough because we know the issue is with the Fibonacci calls, right? Fibonacci tree calls. Remember that problem. Recursive calls. Right? Yeah. So this is the issue, right? That's the problem here, right? We have this tree. So what's the solution? Let's see if we can implement this, right? So let's see if we can do memorization, right? Let's see if we can do that. I don't know if AI is going to help me. Let's implement. Let's implement Fibonacci with memorization. Let's see if we can do this. I don't know. Right, long Fibonacci memo, right? So what happens, of course, is we need to pass a memo, right? And then return memo, right? And then we need to pass it along. So what's happening, of course, here is you need to pass a pointer, right? Because why? Well, so basically sharing this memo, that's the easiest way to do it, right? So let's see about this one here. The problem, of course, this is, right? What's the problem with this, right? Is this approach? It's a pointer, right?
Yeah.
Yeah. Well, but what we are doing here, well,
we are accessing
no.
this element.
Yeah, but we don't know how long this, we just got one pointer, right? So we are basically playing with fire here, right? So it's up to us here, right? That this actually is correct maximum size, right? So basically, right, we're sort of depending that this is we gave them good enough big array, basically, right? As otherwise, we'll be in big trouble, right? So this is right, right. So this is So this is again. This is extreme. Again, this is very dangerous if we do not know the limit of n. We don't know how much space, how big our array is. So yeah, so what I would suggest actually would say max size of array size, basically, because this is decaying pointer, right? So this is very unsafe, right? I mean, so explicitly we'll have to do the size, right? You don't have, because otherwise, because we are just, like I said, C++ will let you do it. It'll let you shoot yourself in the foot, right? It will, okay, it checks, okay, this is not the worst. I mean, it could return any value, right? But here, this part here, you're writing some memory, right? You need no extra, you have space, right? Right. So size, right? If n gets too large, I would say max size. Max size, yes, size would be a good idea, right? The size of memo size, yeah, memo size, right? Or size t, right? Size t. Yeah, this is actually would be a good size t is actually unsigned long, right? So what we'll do is basically I don't know, if check if we have not gone over the memo size, right? Return none or exits failure, right? Right. Could print something here. See out all out of memo size too small, right? N is at least n, right? So this is safer, of course. So now, yeah, we have this extra safety check at least. Assuming nobody lies to us about the size, right? We would calculate this. So let's do this. Let's allocate it here, right? So let's allocate some memo, right? I'll call this. Let's add another flag, right? Fib memo. Fib memo. Fib memo. Yeah, okay. On here, right. N plus 1, that's pretty safe. That sounds good. Yeah, we need to initialize linear, right? We need to initialize first two values, and then we should be able to be good to go, right? Right. So size here, n plus 1 is of course safe, right? This allocates on stack, right? For this, for main, right? Let's see this works actually, right? Or a heap. We should probably do. Let's see this works. That's kind of dangerous too, right? Where it allocates, right? Do where exactly, right? It's function, right? You're going to be passing it along, and we are going to be modifying it, right? Initialize it, right? So this is going to be a little messy, right? Let's see if this works actually. Right? We have all -1. How did we check -1 here? We checked. Yeah. Okay. Okay, so we need to add the size, right? Size, memo size, right? Yeah, this is always going to be passed along, right? So we need to add this, right? Like, of course, if you are under, like you're doing a midterm or an exam, right? Then you don't have time to think about this, and you will probably commit this to be a mistake, not to leave this out. All right. Now this looks okay. Again, we have reasonable guarantees, right? But again, this pointer, we are going to be modifying it, right? That's the whole essence of this memo, right? Because it's recursive, right? We can't, I mean, we could copy it each time, but that's kind of silly, right? We have it it's kind of like a global, basically. We're using this memo as sort of like global value, right? Okay. So I wonder if this is going to be safe. Let's see if compiler complains. I'm not 100% sure it's going to be safe. Nope, okay. Oh, no, okay, size. Okay, yeah, so size. Okay, so this needs to be cast to the size to, I think, yeah, to cast it. I think, yeah, this. How did it, was it like this? Oh no, I think it was like this. I forget now. Let's try it one more time. No. And where is it? Ah, it's in a. Where do we compare it? Line 43. Let's do 43. Okay. Ah, here we go. If n. Right. So n is long. Size t is unsigned long, right? So theoretically, we could of course make this also size t, because size t is basically long, but it's signed, it's unsigned. Or we could say, okay, this is size t. We could do this, right? We could, assuming it's positive, so this should be completely, should be enough. Let's take a look if this is okay. All right. So let's see if we can get instruction. All right. Oops. Oh no. Fact something. All right. Fib memo. Let's do fib memo. Let's do so fib. We did what? From how far did we go? 30? No. 40, right? 40 was okay. Fib memo. All right. That's much better. Can we do 50? Yes. Can we do 60? Yes. All right. So we successfully time fib, right, 40. We install 0.7 seconds on fib memo. 40 will be right. So huge difference. Again, going back to, it's basically dynamic programming, right? As applied top down, basically we are caching the solutions. All right, so that's good. So essentially we are caching. Very good. So before the break, what do the slides show? Okay, so we have our recursive solution, right? We solve this, right? So we have recursive functions on infinitely many copies of itself, really, right? So going back to directly recursive, right? So there are a couple of definitions here. A function that calls itself is directly. So what's indirect recursion? Now is your answer. Function that calls another function, and eventually some other function will call the original. So it's like a chain, right? So eventually some function calls the original function, and of course you keep going. Well, again, assuming there's no base case. If there's base case, eventually you stop, right? That's possible too, right? So of course it's much easier to make a mistake. Somehow if you somehow make a call the function from the you forget that you call this function actually was calling the other function, right? Maybe five levels deep. You call the original function, and then you're surprised that you have a loop, infinite loop, basically, right? And there's another term called tail recursive function. Right, last statement is a recursive call, right? Not all recursive functions are recursive functions, right? So there are certain things you can be optimized if the function is tail recursive, actually, right? It can be important sometimes, quite important, right? So infinite recursion is basically you keep forever. Of course, eventually you run out of memory, your stack space, right? So again, solve this, well, it's like easy. Okay, realize what the problem requirements are, determine what the limits are, identify the base cases, identify the general case. So we have our Fibonacci. What else could we do? I would like to do, let's see, I would like to see if we can do a big number version. I want to see how large a number can we get. Let's implement a large version, large number. Let's add a big number library. Do we have one? I think this, it's actually included, actually. Okay. Large number support. Let's see this, if we can do this. So let's, where's our PBM766 here? Big number support. I have to do it by hand. I think there might be a good one right now. See, people reference. Yeah, numeric limits, fundamental types, big numbers, right? But this is just somebody arbitrary length integer. This is somebody made, right, on GitHub, right? They are quite slow. There's somebody asked on Reddit why it's not built in. As I thought, it's not built in. This is just somebody who wants to get some coffee for free, right? That's who is Ruskas. Maybe he's Lithuanian, no, or Russian, Anatoly, right? So I don't know, right? So that's his library, right? I don't know if I want to trust him. I don't know, right? But he's still active, right? He's still active. Lime oats, right? So relatively active, but not a big one, right? 7 years old, right? So it works. I could include it from GitHub, of course, but right, yeah. So big int, right? Of course. Somebody says never need. Well, some people say they don't never need in C++. They don't need big integers. I don't know, right? All right. So obviously, again, because of course we don't know when we how much we usually don't need these truly large numbers, right? Truly. So long double is actually only 828 bits. It's only like 80, right? So basic answer is that so we would use here's GM. Yeah, I think I used this one long time ago. Yeah, Ganapu, right? So this would be the one to use, right? Because of course this has a very old storage history, right? That's a use. This is made in 1991. Can we actually include it? Let's see. Only problem is how do you include it? You need, of course, you need the actual DLLs, right, for linking. So you have to download the tar file, right? Right. So we can use this to compute billions of digits, right? But again, it's fun for mathematicians, but not so fun for regular work because you don't really need it, right? So CSD doesn't have it anything bigger. Let's do maybe we'll go to the break. We could do probably factorial with what? With we could use vectors. I guess we could use vector, right? Let's use vector to allow saving of to simulate big numbers when calculating factorial. Right. So that's a possibility, right? We could have byte vector, but we probably need to create our own library, right? That'd be also a kind of task. We could. Okay, but let's take a break and we'll continue at 12:10.